All right, who is the class president? All right, do you mind if I talk to you very quickly over the break?
Yeah.
No, not a bad thing. Not a bad thing. We can find out and touch base with you. All right, so you completed the midterm exam. Got it submitted. Excellent. We're going to transition now from the descriptive part of statistics to the inferential part of statistics. So just a couple slides, kind of get us all on the same page. So we're able to convert from just describing what we see to determining whether what we're looking at is actually real or due to random chance. To make that conversion, let's bring in some of the other things that you guys have been talking about or thinking about or studying about. Anyone take any English literature classes? All right, do you have an idea of who is there on the left? Who is that guy?
Shakespeare?
Not Shakespeare. No, this is a couple hundred years after Shakespeare. Well,
My
you guys
bad.
are really young. Any idea? Have you ever heard of The Portrait of a Lady? Portrait of a Lady? It's a novel. Yeah, beautiful novel, right? Henry James. That's Henry James on the left. And on the right, that's his brother, William James. William James is one of the greatest philosophers we've had in modern times. It's actually The Ambassadors. Henry James also wrote The Ambassadors. It's a fantastic novel. In fact, Henry James is considered to be one of the greatest novelists of our time. And his brother, William James, is one of the greatest psychologists and philosophers of our time. So his brother was actually one of the professors at Harvard Medical School. And he influenced someone that kind of influenced some of us who grew up in Pittsburgh, Pennsylvania. Do you remember this quote? 3 things in human life are important. First is to be kind. Second is to be kind. Third is to be kind. That's Henry James. Henry James is the one that said that. And then his brother is the one that said, act as if what you do makes a difference, because it does. Right? So again, these are the, it's a very unique family, but they also kind of represent what was happening during this time in America. Not so much in Europe, but at least in America. Well, they had an influence on someone who was influenced by someone else. If you look at the style of the painting here, do you have an idea? Would you like to take a guess who painted this?
Picasso.
Oh my goodness, who said that? Yeah, Picasso. And you'll notice that in Picasso's time, and especially in Europe, there was this movement. They called it Cubism, and they tried to influence these geometric shapes to kind of give you multiple perspectives on whatever your subject was. And the subject here is an actual person. Her name was Gertrude Stein, and she was born in Pittsburgh, Pennsylvania, which is where some of us grew up. Ended up moving to Oakland, California, but then her brother said, no, you gotta come out to Paris, live with me, and kind of get involved with Picasso and everyone else who's kind of really generating this very strong, very vibrant art scene. Okay, so Gertrude Stein, she actually didn't like this painting because she had to sit there was like 80 to 90 sittings she had to go through just for him to get this. But Gertrude Stein is someone who actually spent a lot of time thinking about what makes us appreciate art. And that was part of what allowed the art movement to convert from some more contemporary fashion to what was considered modern art. So Gertrude and her partner are actually the ones that created the very first museum of modern art. So if you go to MoMA in New York, which is where a lot of them actually were based, or many of the other museums of modern art, it's due to their influence. But anyway, she had an interaction with William James. Remember the psychologist at Harvard? Gertrude was one of his students. And she had an interaction with him that kind of reminded me of some of the emails I got over this weekend regarding your exam. This was this was her exchange. This is what she wrote to him. Dear Professor James, I'm sorry, but really, I don't feel a bit like an examination paper in philosophy today. That's it. His response was, Dear Miss Stein, I understand perfectly how you feel. I often feel exactly that way myself. So I got some of your emails this weekend, like, this is the last thing I want to be doing. And why do I have to deal with this question that has no answer? I think I got the right answer, so why is it being marked wrong? And there are just all kinds of questions this weekend. I felt really bad for you for that question, and also that you were trying to tackle a stats exam over the weekend. I just want you to know I empathize with you, because that's the last thing I'd want to be doing too. However, this is a process you must go through. So I think you did fine on the exam. That one question is going to be thrown out. We'll be fine. The real challenge now is trying to make this conversion, which is what Gertrude and the James brothers would all hope that we'd be able to do, and that is learn to observe, to find a difference that really matters. And that's what we're trying to do with clinical significance and statistical significance. You remember that one expression, a rose is a rose is a rose? That's Gertrude Stein. She wrote that. She also said something that I think is quite apt to what we're going to do today, and that is a difference. To be a difference, you must make a difference, right? It's supposed to be you. It's also supposed to be the stats that we're trying to figure out. Hey, this difference that we see, is it real? Is it statistically significant or not? All right, so a couple of things that we want to do before we whip out the Jamovi and kind of figure out what these p-values are telling us. So there are two main ideas that I need for us to kind of keep in mind as we try to test hypotheses. The first is going to be exhibited by this little example. About 4 cards here. There's a vowel, there's a consonant, there is an odd number, and there's an even number. Here's the idea, and this idea is sort of like our hypothesis. If a card has a vowel on one side, then it has an even number on the other side. How would you test that idea with these 4 cards? So if these 4 cards were sort of like your sample, right, from a population, or your population, how would you test this idea in this population of cards? What would you actually do? What would your methods be? So again, if a card has a vowel, for example, like a name, if a card has a vowel on one side, then it has an even number on the other side. So here are 4 cards, see their sides, how would you test that?
I'll compare A and 2.
Okay, so you would...
I'll compare A and 2.
You would compare card A with card 2?
Yeah.
And how would you compare?
Well, I don't know, the values, flip it around if it's a...
Okay, so you would flip the card and see what's on the other side. Okay, so for example, if you found this card, you came across this card, it's got a vowel, A on one side, and you flip it over, what would you be looking for?
It has to be an even number.
You'll be looking for an even number. Okay, so that's one method, that's one strategy. Anyone else?
I would flip the
Yes.
2.
So is that based only on those 4 cards or the whole?
Yeah, these 4 cards are our population of cards.
Okay, so it doesn't, so the numbers don't extend past that?
No.
Um,
It's a good question. Does it help you answer how you want to?
I thought you had like, because there's 5 vowels, so I thought you had like A, E, I, O, U, and then
Nope.
2,
Nope.
4, okay.
Just as long as you know what a vowel is and this is your population, could you test this? Anyone else? Yeah.
I would get an even number and flip it over.
You'd get an even number, so you'd find a card where the side that you're looking at has an even number, and then you'd flip it. What would you be looking for?
A vowel.
You'd be looking for a vowel. Okay, anybody else? Okay, so what we're hearing so far, our methods are quite intuitive. That is, we're looking for what we think will confirm what we're trying to find. But in science, what we're taught to do is to do the opposite of that. Don't look for evidence that confirms what you're looking for. Rather, look for evidence that rejects the opposite of what you're looking for. Okay? And it's to avoid something called the confirmation bias. All right, so here's Karl Popper, who's one of the forefathers of the scientific method. And this is what the confirmation bias is. It's a type of cognitive bias, that is, it's a quirk, a systematic quirk in our thinking, like a blind spot. And it's a form of selection bias. And in essence, what it does is, it's the tendency to only seek out information that confirms or conforms to pre-existing ideas or viewpoints. Okay, so if we already have in our mind, so if a card has a vowel on one side, has an even number on the other side, if that's our idea, a confirmation bias would be to look for evidence that confirms the idea. That is, flip over the A, implying an even number, or flip over an even number, implying a vowel. But to avoid the confirmation bias, the scientific method says, take this set right? And instead of looking for evidence that confirms it, look for evidence that disproves it. So find the A, the vowel, flip it over, and instead of looking for an even number, what should you look for? Odd. So what you're hunting for now is evidence against this. So if you find evidence against this, then what will you do with this idea?
For it or against it?
Yeah, if you find evidence against this idea, so you
Reject
flip
it.
out the A and you find a 1 on the other side,
Reject it.
you would reject this, right? And how many of those would you need? Only 1. So that's why it's a far more elegant method, where we don't have to use a whole population of cards, just the sample, and that is to look for evidence against the idea. And if you find it, then you get to reject it. But if you don't find it, sure, you might be in a situation where do I need to find more cards? Do I need to extend my search further? Maybe you do. Maybe you need to. Or maybe we have an idea of how many is enough for us to stop. I don't have to keep searching. I can't find evidence against this idea. And if I can't find evidence against it, what will you do? Keep it. You'll keep it. Because I don't find any evidence against it, so I'm going to hang on to it. That's how we do it in science. Okay? So it's a little tricky, but you'll get the hang of it. Right?
Interesting.
That's big idea number 1. All right? Any questions about big idea number 1? Yes?
So the confirmation bias is the tendency to look for things that are going to confirm a thing, to confirm your idea, but
Exactly.
you just gave us the tool to not do that?
Right.
Sorry, I just want to make sure.
Yeah, absolutely, absolutely. So again, confirmation bias says, this is my idea. So all of you are proposing research and you have a hypothesis, that is some kind of effect or difference that you hope to be able to find, that an exposure is related to something else. But instead of trying to find evidence for that, what you're going to do is trying to find evidence against the opposite of that. So you're going to find evidence against what's called the null hypothesis. So the null hypothesis says, hey, all these differences that you find, they're not real. They're just due to random chance. And what you're going to try to do is go into that population, take out a sample, and hopefully your sample will have the evidence against that null hypothesis. That says, nope, these are not random differences. These are really big differences, not likely to be random. Therefore, then you get to reject the null hypothesis. Okay? So we're getting there. The second big idea is, look at these 3 cards here, right? You've got a 2, you've got a 4, and a 6. Now, the question is, what's the rule that these 3 cards are demonstrating? In order to test that, tell me what you think the next card should be. Okay, now some of you are saying 8, which would, and what rule would these 4 cards be keeping or demonstrating? Sorry? Okay, multiples of 2. So if you think that when you see this pattern out in nature, you say, oh, I think these are multiples of 2. Therefore, I think the next card ought to be an 8, right? That's what you're hoping. But since I know the rule, if I come back and tell you, nope, that's not the rule, then you go back and say, okay, you look at this pattern again, and you say, what else could it be? So I'm telling you, 8 would satisfy it, but that's not the rule. So what's the rule?
36.
36? Okay, so if you put a 36 here, then what's the rule that you think these cards are keeping? Okay, a square. 36 would keep the rule, but that's not, it would satisfy the rule, but that's not the rule.
I wrote the rules just to be a pair number.
To be a,
Pair number or even,
And
pretty much an even number. So
an
it can
even
all-
number?
it
Okay,
can
so you
be
can pick any even number, so maybe, what would you want to put here?
Whatever, it can be anything.
8? 12? Okay, that would satisfy the rule to some degree.
Could it not be any number?
No,
No?
No.
Okay.
okay? Because let's say the next 2 cards would be, let's say 12, and then you would say 5, and I'd say nope,
we don't.
that would not satisfy it.
Sample.
It was incrementing. It's going higher.
Exactly, so here it is. They're just increasing. The rule that I'm demonstrating here is just increasing numbers. So it could be 2, 4, 6, 6.1, right? So when you're looking at these patterns, the second big idea I want you to think of is, don't think of the most complicated or the most elegant rule. Think of the simplest rule that would probably, account for that pattern. Start there first. So number one, first big idea is, don't look for information for what you're hoping for. That's a confirmation bias. Let's look for information against the opposite of what you're looking for. And the second big idea is, when you see these patterns, think of the simplest rule that would account for that pattern first. Test for that simple rule first before you go on to more complicated ones. On the same page so far? All right, those are the two big ideas that we have to keep in mind when we test hypotheses. Then the third thing I want us to be thinking about is context, because there are going to be some gaps as we try to think about testing hypotheses. We need a metaphor or analogy that will help us fill in some of these gaps. And the best metaphor or analogy that we have is our court system, at least our criminal court system. So when someone is on trial, at least in the U.S., they are assumed what?
And
I'm not sure what state you're from, but no, not guilty. Innocent. You're assumed to be innocent until proven guilty.
Everyone's guilty.
Wait, Kelly, where are you from?
Nebraska.
Nope. You guys do things a little bit differently in Nebraska?
A lot different.
A lot differently? We'll give you a pass there. No, innocent until proven guilty, right? And when someone has presented, or at least the prosecution has presented enough evidence, what's the verdict? Hopefully.
It depends on the evidence.
No, it's enough evidence.
Guilty.
Guilty. What if they don't produce enough evidence? What's the verdict?
Not guilty.
Not guilty, not innocent, not guilty, just as you say. So the same way for testing hypotheses, we either reject the null hypothesis, that's guilty, or we fail to reject the null hypothesis, it's not guilty. We never accept the null hypothesis. We never say someone's innocent after they've gone to trial. We only say not guilty. All right, in terms of the role that a judge and a jury play, do you understand what the judge and jury do? And then would you be judge or jury when you're testing a hypothesis? So what's the judge's role in a criminal court case?
Come to a conclusion.
Sorry?
Come to a conclusion.
Come to a conclusion? Yes, but not on their own. The jury's supposed to help with that, right? It's supposed to be judged by a jury of your peers, not the judge.
maintain order of the trial.
Okay, maintain order of the trial, and then back.
Well, yes, to make sure that everyone is following the same rules.
You got it. Maintain order and following the rules. So there's a whole set of proceedings and guidelines that must be followed for a fair trial. And it's the judge's responsibility to make sure that that happens. The judge is supposed to be impartial, to make sure that everyone follows the rules. What about the jury? What's the jury's responsibility?
Show up.
Show up, yes. And in addition to that,
Decide whether
decide whether evidence and
Guilty or not guilty?
guilty or not guilty. But before they arrive at a verdict of guilty or not guilty, what are they supposed to be doing?
it's supposed to be like bias.
Right, weighing the evidence, right? Weighing the evidence to determine whether the prosecution has done their job of presenting enough evidence. Then there's a special term after that, enough evidence. It starts with beyond reasonable doubt. That's the threshold. It isn't they presented all the evidence that kind of condemns this individual. No, they presented enough evidence so that you pass that threshold of reasonable doubt that this person is guilty. That's the same game we play in science too. We're not looking for the entire population. We only need a sample large enough to present enough evidence for us to say, this is enough evidence to suggest that random chance is not responsible for what we're looking at. This other hypothesis is responsible. This other hypothesis is guilty. And in this instance, that hypothesis, called the alternative hypothesis, is what you actually want. You want a guilty verdict in science, typically. There are times when you want a not guilty verdict. Okay, so there are two hypotheses. The first is called the null hypothesis. Get a bit warm here. And then the second is the alternative. These are the only two hypotheses under consideration. Just like in a criminal court case, there are only two realities that are under consideration. Either the person is guilty or not guilty, right? So in terms of hypotheses, we are concerned about the null hypothesis and the alternative. What you want is called the alternative hypothesis. That's what you want, typically. But the confirmation bias says, can we look for information? Can we look for evidence in favor of what we want? Are we allowed to do that? According to the confirmation? No, we cannot do that. Scientific method says you cannot do that. To avoid the confirmation bias, I can't test my alternative, I should test the opposite of it, the null hypothesis. Okay, so what we want is the alternative, but I can't test the alternative because that would be finding evidence in favor of it. That's the confirmation bias. So I test the opposite, called the null. So in a political debate, like the one we're in right now, when a candidate gets up and they start really going after ideas, it's not typically the other opponent they're going after. They're going after these other ideas. And the way they present these ideas is as what they call a straw man. Now, as you can imagine, as you get that mental figure, a straw man is something that's fairly weak and easy to knock down. That's why you kind of raise it up and then you knock it down. And oh wow, this individual is so strong or so gifted. Because you raise up these straw men and then you knock them down. You raise up straw man, knock it down. Raise up straw man, knock it down. It seems like, wow, this person is really winning this debate against this invisible person. In science, we do the same thing. It seems like the null hypothesis is an easy hypothesis to knock down. That is, oh, all these differences are due to random chance. Now, sometimes that's true, but oftentimes that's not true. Because what we're going to assign as random chance, like this straw man, it's actually going to be a wide portion of a distribution. So our straw man here in science actually has a bit more weight than the straw man in a political debate. Okay, so it's not so easy to knock down the straw man scientifically, but it's possible. Yes?
I'm trying to kind of understand the difference between null and alternative, but you know when we've done like in biology class when we did in lab
Yes.
hypotheses and experiments.
Yes.
That's what is that the alternative?
Okay, let's take two steps back because you're right. We've done the chemistry labs, OChem labs, inorganic chemistry labs, biology labs, and physics labs. And in these labs, the first thing we're always taught to do is what? The very first thing, before we even get to the hypothesis stage, is what you were doing for like the past 4 or 5 weeks. Yes, looking. Make an observation. Once you make that observation, then your next task is to determine, is this observation, are these real differences, or is what I'm looking at due to random chance? That's where we now have to figure out how am I going to test that. But first, you've got to make an observation, see something. Then once you see something, then you say, okay, what I just saw, is this real or not real? You know, you wake up, I don't know, the part doesn't happen to you. It didn't happen to me, I'm just saying. You go downstairs, you see something around the corner. Like, whoa, is there a ghost in here? Was that real or not real? You gotta make a decision. How are you gonna test? But you gotta figure out, was this real or not real? So you're looking around, saying, whoa, is that real or not real? Null hypothesis says, not real, that's random chance. Alternative hypothesis says, no, that was real, get out the house. Right? Anyone see Get Out?
Oh, yeah, I was going.
Go now. So, is this real? That's alternative hypothesis. Is this real, or is it not real? That's null hypothesis. Now, the null hypothesis doesn't call it not real. It says due to random chance. These are variations that are not due to some process that you should really take note of. It's just normal variation biologically, right? We always bounce around there.
So we're doing the same thing, the alternative hypothesis.
Yeah, the alternative is the real, that's a real difference, what you observe. Because you can't change what you observe. You saw this. The question is, was it real or not? If it was real, then that's an alternative hypothesis. If it was not real, then that was due to the null hypothesis. Oh, I was up too late, it's a figment of my imagination. Or the window was open and so the curtain was blowing, it's not real. All right, so now that we have an idea of alternative hypothesis and null hypothesis, we have a decision to make. We have to figure out how rigorous am I going to be when I test this hypothesis, right? When I try to determine was this real or not real. There are two things I want you to think about when we say, I've got to make a decision as to whether this is going to be a 1 or 2 tailed test. What does that mean? When we test these hypotheses, right, is it the null hypothesis that explains this or the alternative? We have to take that qualitative statement and make it quantitative, meaning we make a distribution for that null hypothesis. So when we say, is the null hypothesis responsible for that? We say, okay, well, if the null hypothesis is responsible for that, first, it will have this distribution, and it will have a mean right here. Okay? For it to be due to the null hypothesis, you have to be anywhere in this white zone, not the gray zone. Anywhere in the white zone says null hypothesis was responsible. It wasn't real. But if I find, that is my observation, if I take my observation and I put it in this distribution, if my observation ends up in the gray zone, then it was real, meaning null hypothesis could not have done that. I say this because on the y-axis, which we don't have here, that's frequency. And you'll notice that these shaded areas are quite small compared to the white areas. So what we're saying is that the frequency or the likelihood that null hypothesis would have made something down here or up here is very low. So you're making a probabilistic statement that the likelihood or the probability associated with null hypothesis producing what I saw is really low. So, come downstairs, you get a glass of water, you see something over there, right? Yeah, maybe it was. You get the glass of water, you turn around, that thing is still there. All right, so now you're out here, and you got to make a decision. Probabilistically, if that was not real, it shouldn't still be there. Now I'm leaving because my hypothesis says that's real. I'm out of here, right? That's what we're trying to do. You make everything qualitative, quantitative. So now you can figure out what you want to do. Hope I'm not freaking anyone out. This is all just riffing with you this morning. All right. Okay, so there are two types of rigor that we need to make a decision on. One, am I going to say there's only one part of the distribution that says it's real, or will I say there are two parts of the distribution that say that was real? There's a question.
Yes, sir. Can you just repeat? So if it lands in between or in the white, you said the null hypothesis, we reject the null hypothesis?
Right, so this whole distribution is due to the null hypothesis. But we say this null hypothesis is saying the mean could be here, or the mean could be way up here, or the mean could be way down there, really anywhere on here. And what we're saying is, okay, that's too much fluidity for me. I'm going to put some thresholds in here. I'm going to say this zone and this zone. If you end up in this zone or that zone, that is what I'm observing, is I put it in the null hypothesis distribution. If you end up down here or up here, I'm going to say, no, the likelihood that null hypothesis is responsible for that is really low. But if it ends up anywhere in here, in the white zone, you say, okay, well, that's more likely, right? That's what we're doing. Now, the one in the middle says a two-tailed test is where you say you've got two regions of the distribution that could reject the null hypothesis. These other one-tailed tests say there's only one region. And my argument for you is, let's run two-tailed tests because they're more rigorous. And you say, but how are they more rigorous? More rigorous. I say, well, do you remember when you're learning to drive and your instructor said, okay, that's great, you're looking out the front windshield, but there are cars behind you too. So please look out of your rear view mirror occasionally, right? You do the same thing in distributions. Don't just look at one portion of the distribution to reject the null hypothesis. Keep in mind the other end too. So let's say you came up with a new drug, a new treatment, you think it's better than the standard. That's great. We can conduct a test to see if it is better. But what should you also keep in mind? What's the other possibility for your new treatment or your new test or your new drug?
Not better.
Right, it could actually harm people significantly. So while we're up here saying, yeah, we hope this does better, I hope it really ends up here, we're also saying, but there is the likelihood that it might go in the other direction. So I'm gonna test for that at the same time too. That's more rigorous. It's a better way to draw it too, right? If you focus on only one region, you need to have justification or rationale for doing so, for ignoring the other end. So maybe there's a biologic phenomenon that might explain that. That's rare. So I'm always going to say when you are conducting tests, run a two-tailed test, not a one-tailed test. Because it's more rigorous. The other way it's more rigorous, now I'm asking you to think more quantitatively. If you think about the numbers down here, the size of this gray zone is 5%. It always totals 5%. So here in the one-tailed test, that means 5% of this whole distribution is down in that gray zone for the one-tailed. But for the two-tailed test, I take that 5% and I have to split it between two zones. So this 0.05 then becomes how much in each tail? 0.025 or 2.5%, right? So now, because I've made these gray zones smaller in the two-tailed test, that means I've made it harder to actually get into the gray zone. Because I've made it harder, that means it's a more rigorous test. So these are two ways in which the two-tailed test is more rigorous than a one-tailed test. It's more rigorous because one, I'm keeping track of two zones instead of just one, and also I'm making it harder to reject the null hypothesis because you now have to be more extreme in order to get into those gray zones. With me so far? Getting some head nods, some blanks here. All right. We're going to keep going. No questions? No questions? Comments? Yes.
Is that why we say if the p-value is below 0.05, we reject the null
That's
hypothesis?
right. Because what you're saying is when the p-value is less than 0.05, you're saying if that score, when it gets converted to a probability, puts it into the gray zone of this distribution, then we're going to say the null hypothesis distribution is probably not likely for that. It probably belongs in another distribution where it will be closer to the middle. Yes?
Are those numbers at the bottom of those standard deviations, these scores? Or
Very good question.
Z-scores?
These numbers down here are what are called standard scores, and they're like the z-scores. So here, you'll notice that the z-scores, or the standard scores associated with this 5% alpha in the two-tailed test is 1.96. And you'll notice that the 1.96 is bigger or more extreme than the 1.65 for the one-tailed test. But it's still, they're both still at 5%. Again, that's because 5% in one tail, you don't have to be as extreme when now you're at 2.5% here and 2.5% here. Now, you're clinicians, so you'll notice that, wait a second, you copied and pasted here, and the size of these gray zones look the same. Ignore the size and just focus on the numbers. But ignore the relative size because, yeah, they look the same. This should really be 2.5%, and that should be 5%, but they look the same size. Good observations, good comments. All right, moving on. I want you to also keep in mind that the terms that you're using are now considered to be part of the general public lexicon or language. This was an article that came out in Reuters. It was published in London, where they're talking about people who are saying, you know what, I've got cancer, but I think it's related to my overexposure of Roundup or use of Roundup. And you'll notice that as this article, again, this is general public, the article, they're using terms like not statistically significant. That is, they expect the public now to understand what that means. So here they're saying, said that there was some evidence of increased risk of acute myeloid leukemia among the highest exposed group, but added that this association was not statistically significant. This is in reference to a study that at least the other side is presenting. I just want you to understand, again, these terms now are considered to be what most people should understand. All right, let's take a half step back to the context we were talking about before, our criminal court system in the US. I've got two states here. One is a decision that we make, the other is what the truth actually is. So if the truth is that the person on trial did not commit the crime versus they did commit the crime, we want either of these two states to match up with our decisions, like a verdict of guilty or a verdict of not guilty. And if we keep this 2x2 table in mind, we'll be able to understand what a false positive is, what a true positive is, true negative, and a false negative. So they did not commit the crime, so not guilty. Our verdict should be not guilty. So if that happens, that's a correct outcome. That's a true negative. Fantastic. Everyone goes home a winner, the court system and the individual on trial. They did commit the crime, and the verdict is guilty. Correct outcome. That's true positive. Again, everyone's a winner. Trouble happens, though, when we have errors in our decisions. So when we decide that someone is guilty, or when we say that a hypothesis, that there's a real difference, but in fact, they did not commit the crime, or the null hypothesis is true, that's called a type 1 error. So that alpha that we've been talking about, that alpha is an error. Alpha is an error. So when we say alpha is 5%, we're saying in this study, I don't really want to have more than a 5% chance of making an error. Well, which error? The error where I say someone's guilty when they're really not. The error where I say there's a real difference when there really isn't. Okay, so that's alpha. When you start thinking about it as an error now. There's a second error too, though. That's called beta, or type 2 error. This is where I say, oh, the person's not guilty, but they are. They're getting off. That is an error. It's called beta error, false negative error. So I run a study and I say, no differences, but there really is. Like, there really is a difference. Just in your study, you didn't find it. So when you say, no difference, or not guilty, that's what you said, that was your decision, but unfortunately, that wasn't the truth. So these errors do happen, we just try to keep track of them and assign a probability to them. What's the likelihood that I'm making this kind of error? What's the likelihood that I'm making this kind of error? None of our decisions are perfect. And more importantly, in an environment of uncertainty, we never really know whether I made an error or a correct decision. Best I can do is assign a probability to it. All right, so finally now in our stats case, we're going to swap out and say now the null hypothesis is when the null hypothesis is true, and when the null hypothesis is false. These are our true states. Do we test the alternative hypothesis? No, we never test the alternative. We only test the null. Only test the null. So if the null is true, let's see what happens. And if the null is false, let's see what happens. So when the null is true, and I fail to reject the null, that is, you end up keeping it, that's a correct outcome, true negative. The null is true, so don't reject it. You don't want to reject something if it's true. So I fail to reject the null when the null is true, great. When the null is false, what do you want to do to it? Reject it. So if the null is false, and we can only test the null, then you want to reject it if it's false. Great, that's a true positive. I found something. But when the null is true, and I get rid of it, that's an error. That's that alpha error. When the null is true, I should stay there, but instead I reject it and say, no, this drug really works. No, this treatment really works. But in truth, it really doesn't. Because again, the null says, yeah, you'll see a difference, but it's just due to random chance, not due to a real effect. That's a type 1 error. That's a false positive. And the type 2 error, the beta error, is when the null is false, but I fail to reject it. I'm going to get rid of it if it's false. But I don't get rid of it. I keep it. That's a beta error. The real finding, I should reject the null, but I don't. I keep it. I fail to reject it. Okay, so study this 2x2 table. You want to get comfortable with it because it's not just statistics. This is actually every day. This is real life, this 2x2 table. And if you can reduce a lot of your complex decisions where it seems like you have too many outcomes. You can reduce it to a 2x2 table where it's either A or B versus A or B. You've now simplified it, and you're going to make it a lot easier to make your decisions or figure out what happened to your decisions. All right, fantastic. So what's the step-by-step process we're going to be following in order to test these hypotheses? This is what we do. First step, we make some assumptions. What's the purpose of making assumptions? Do you guys make assumptions? All the time? Boy, that came quick. Would you like to share with us when you make some of your assumptions? Not really? That's all right.
Always.
Always? Well,
Like-
when do you feel most comfortable making assumptions?
Like, it's 5 p.m., there's gonna be traffic outside.
5 p.m., True, there's going to be traffic.
Yeah.
It helps you make a decision about how you want to proceed. in terms of traffic. A network.
Music? I assume no texting, but
No texting? Okay. Anyone else? What kind of assumptions do you make? You can share. This is a safe zone.
If you eat an apple, it's gonna be sweet.
You make an assumption when you've been through the situation and
Okay, so you make assumptions when you have some history, you're familiar. Okay. Alright. So assumptions work really well when we have data to rely on. Interestingly enough, though, and these are called heuristics, assumptions work really well when you don't have a lot of data to go on and you need to simplify your decisions. So in both of those scenarios, assumptions are really helpful. You don't want to spend all the time kind of going through that sheet and figuring out what to do. You really got to kind of cut in and say, you've got to make a decision, you've got to move on. All right, so what we do is we're going to make assumptions because we can't be testing forever to make sure that this situation perfectly matches up with another situation. So we're going to assume so that we can move forward with our testing and hope that our assumptions aren't so weak that we start making decisions or conclusions that don't fit the underlying data. After we make our assumptions and meet test requiremements, we're then going to state what our null hypothesis is. What are we actually testing? And it's not what we're interested in, it's the straw man. We're going to test the straw man and see if we can knock it down. Then we're going to figure out what our sampling distribution is. And the sampling distribution is like, look, here's where I want to go. I need to get the right map to tell me how to work, where I want to go. So if you have the right map, those mile markers will match up. Right? If you have a wrong map, an outdated map, you'll miss exits. You'll end up where you don't want to go. So selecting a sampling distribution says, okay, it looks like with my variable, the underlying distribution is a normal distribution. So that's the map I'm going to use to kind of figure out what's likely and what's not likely. Next, I'm going to compute the test statistic. Jamovi will help you do that, and it will give you a p-value, which you will then have to interpret. These are the steps for testing a hypothesis. Fairly simple, and the more you do it, the more comfortable you get with it. How are we doing? We good? Need a couple minutes? Yeah. Let's take 5 minutes, and let's come back, and then let's actually start testing hypotheses. Sabine, so next one. Is there a possibility?
not right now anyways.
Monday afternoon.
Yeah, let me grab
That's what happened to me.
How are you doing today? This one? Right. Or too high.
the only grade one. But you prefer 2 years because
Yes. it's more rigorous. So when you drive, you have a choice. You can drive and say, I'm only gonna look out on my windshield. I'm never gonna look out on my other mirrors. You could do that. We're saying some people just have policy. You have an interest in doing this, but I'm saying just to get both of us just in case.
Are you looking to go to okay. So this one so the no hypothesis is true.
Yeah, so if I reject the null hypothesis, I hope that when I reject the null hypothesis, the null hypothesis is really false. I never know which one of these is actually real. Just hope. I just hope that when I do this, that this is the case. And when I do this, then this is the case. But I don't really know. In case I make an error, if I choose this, then this might be the case. If I choose this, then I get this kind of
How much do you get?
this. Because he's innocent. If he didn't do it, he should be not guilty. So, trying to sort that out.
Yeah, so
Next Monday. So I mean, what it would give you is it would give you next week. So that will take care of what we can do up until
My problem with Mondays is we have clinic. So half the class is clinic. And then we have class from 8. We have class 8 to 12. And then we have grades from Monday.
Well, I could meet with that group, but then the other half of them after.
That would be like
Which we do, lab, and it would just be a lab session. It wouldn't be lecture. How long would that take for Again, it's just
yeah, we have clinic.
so I can make it half a class. No, you want to look at it?
Oh yeah, all mine were yellow. All of them.
Yes. So the other option is for me to just hold the lecture and show you step by step how to do it in the movie, and you guys do it whenever you want.
I think that would be good because we have the only day we'll have available next week is Tuesday because all the other days we have either class all day or and we have clinic all day.
So what I do is I'll record the lecture.
I like it a lot. So I've had that with like a bunch of mouth watches. I can't hear you because of the
Sorry? Yeah, that's okay.
I spit it out after so like I just like I don't like I use alcohol free always, but it was so I use alcohol free like anti texture like all this stuff in it. You know, use it and it still didn't so I think it's just whiskey. But it doesn't hurt, it just like feels like there's like stuff on my gums and I wipe it off and it looks gross, but it doesn't hurt. It just yeah.
So the motor will be there. Then if you have a screw, it's like, I have to never So the one that's furthest to where it's going to be right out.
But there's like barely anything. So
Those are some of the questions.
yeah, I got that. I was getting at certain PowerPoint.
As long as you know that.
I mean, they're not like ideal, but like, if I like you know?
In the sense that we've gone over it, just like kind of.
Oh, I didn't have my glasses.
The alternative
I don't think I see it anymore.
class exams, and I don't like them, students don't like them. But yes, the weight is but it always works out in the end. Which one do you recover on the fireworks bit? I
It is a lot. Oh, you guys know that I went to Mexico, just check out, and then kind of okay, the steps. It looks nicer. Double check to see if it's in alphabetical order. I did put a bit.
All right, let's get started so I can give you a bit of a break before your next class. I'm good. Thank you.
Yeah, gotcha.
Come on, Doc, wake up.
All right, so we're going to run through each of the steps of our guide for testing hypotheses. So have your Jamovi ready. But let's go through each of the steps. So what we've been looking at so far, there's some variables that have been key and core to what we're doing, and that's the proportion of kids receiving preventive dental care. So I want to run through the steps of a one sample t-test. We're going to use a t-test and not what's called a z-test, because we don't really know what one of the metrics is for the population of interest. When you have the mean and the standard deviation for the population of interest, you can use what's called a z-test. As you can imagine, that gives you more power when you know both the mean and the standard deviation. However, in this situation, we only have the mean from the population that we're going to reference against. We don't have the standard deviation. In those kinds of situations, you're going to use what's called a t-test. And the t-test says, let's use what we have either as an estimate or as a proxy for what we don't have access to in the population. Okay? So we're going to use what's called a one sample t-test to compare the rate of the proportion of kids receiving preventive dental care in the U.S. versus the rate of the proportion of kids who are receiving preventive dental care in the UK. That's why we have some data from across the pond. So the Royal College of Surgeons and the NHS put out this kind of data. For example, 1.7 million more people in England have seen a dentist within 2 years than were doing so a decade ago. Now, this was provided as a really positive statistic. Do you have any issues with this statistic? This is from several years ago, about 3 years ago. So again, they said, hey, things are going really well in regard to oral health in the UK. Because 1.7 million more people in England have seen a dentist within 2 years than were doing so a decade ago. Now, 1.7 million sounds like a really big number, doesn't it? But in this class, we were taught to always think about signal to noise. So what did they give us here? Signal, noise, or both?
Noise.
Signal, this is signal. Well, you really don't like these guys across the pond, do you? That's all noise. Rubbish. This is signal. 1.7 million. That's the numerator.
Oh, yeah.
But a numerator without a denominator, not helpful. What kind of denominator here will allow us to know whether this 1.7 million was actually meaningful or not?
The whole population of England.
Population, yes, and more specifically, look what they said. From a decade ago, yeah. So we want to know what was the change in population over this time frame, because they're giving us the change in signal, right? So if they're saying 1.7 million more have access, well, tell me what the change in population was, because if I had a very big change in population, that 1.7 million is not going to look like a very big number. And in fact, that's what happened. So this is what they reported, but I'm looking at it saying, where's your denominator? Because the denominator over this time period makes this 1.7 million look like less than 1%. I'm not impressed by less than 1% over 10 years. So you're telling me less than 1% more are having access over 10 years? That's not great. 9 out of 10 people who wanted to see a dentist in the last 2 years got to see one.
Makes sense.
I don't know. Is that true? What do you think this means? 9 out of 10 people who took the SIM, who wanted to see a dentist, yeah, forget the SIM part, that was my answer, over the last 2 years actually got to see one. Sounds like that might be good. But then when we break that down by age, which is what we're looking at, right? We break that down by age, our kids are getting left out. All right, so almost 62,000 people were admitted to a hospital in England per year because of Toothgate. 3/4 of them, kids. So our question is, well, what's the proportion of kids who are receiving preventive dental care? Because if they're ending up at the hospital, then someone's not seeing these kids. So what's the rate of kids seeing or having preventive dental care? I mean, let's compare it to the U.S. All right, so we actually find out that it's probably about 2/3. Maybe like 67%. 67% of the kids have seen a dentist in the last year or two. So what we're going to do in our one sample t-test is compare what you have for the U.S. and compare it to this 0.67 for the U.K. Just for context, these are the dentists. These aren't other people. The dentists in the U.K., which is 3 years ago, are saying, look, these standards are like third world levels when it comes to oral health. This is a crisis. So the NHS says things are great. The dentists are saying, no, they are not. These are like third world levels. We've got to do something here. So we're going to participate. We're going to participate, jump in the debate, and kind of compare and see if the rates of the kids receiving preventive dental care are different from the US to the UK. So step one, let's make some assumptions. So what are the assumptions for the one sample t-test? First is that the dependent variable is continuous. The dependent variable is proportion of kids receiving preventive dental care. Is it continuous? Yes. It's not nominal. It's not ordinal. It's ratio level. A 0 means no one's getting access to care, right? And then I can measure, let's say, 0.67, 0.665, 0.6213. The question is how, there's no limitation except up to you. So this is a continuous variable or a ratio level variable. Are the observations independent? If you were in Nebraska filling out the survey, well, you can't fill out Missouri's survey too. So our assumption here is that yes, if there were, it'd be very small, but no one was really jumping around to the different states and participating in all the surveys when it came time to collect the surveys. So Nebraska surveys are independent from Missouri surveys, independent from Pennsylvania surveys, independent from California surveys. So yes, the observations are independent. That's an assumption we're going to make. And that the dependent variable is normally distributed. We're going to assume this, but we can also test for it with the Shapiro-Wilk test. Jamovi lets us do that. Okay? You're going to make sure it takes this shape. If it takes this shape, this is our map. And that map will give us the mile markers for where the significance is. This is Not due to random chance, not due to random chance, due to random chance. So if our dependent variable takes this shape, then we're good. We can use this map. If our dependent variable takes a shape different from this, then we should use a different map. Or our assumption should be, it differs a little bit, but not so grossly that I can't make a good decision. Then finally, no outliers. Okay? And when you do your box plot, you can check and see if there are any outliers. And if there are, again, it's up to us to make an assumption as to whether that outlier is influencing the results, so our conclusion is screwed up or not. Next, we want to state our null hypothesis. So if you remember back to our table for what the null hypotheses look like for at least a one sample t-test. Here with the two-tailed test, it tells us we have 2 zones for rejecting the null hypothesis. One-tailed test, only 1 zone. Now our hypothesis, our null hypothesis, is that the means between the 2 countries are the same. UK has 67% of kids receiving preventive medical care. Null hypothesis says US has 67%. We don't believe that because what we observed when we looked at the data was that the US was around what for 2016, which was about 3 years ago. Do you remember? It's from a couple weeks back.
Well,
Was
like
it-
85%.
Yeah, was it greater than 67%? Yeah, we thought it was definitely greater than 67%. So we think we could get away with a test that only looks up here. But we also learned that that's not the most rigorous way to test. The most rigorous way to test is when you say, yeah, I might be up here, but I'm also going to hold on to the fact that I might end up down here. So I'm going to take that 5% that I'm testing at, I don't want to tolerate more than that, and I'm going to split it and say half goes here and half goes here, which means these are the zones in which I'll be able to reject the null hypothesis. So that's my hypothesis. I'm going to say null hypothesis H naught is mu for the US is equal to mu naught, which is 0.67. So mu equals 0.67. The alternative is that mu is not equal to 0.67. So when I'm saying I'm not at 0.67, there are 2 states. You could either be greater than 0.67, that's not 0.67. You could also be less than 0.67. That also satisfies the not equal to 0.67.
Can you repeat that, please?
Sure. When we do a two-tailed test, you write it this way. The null hypothesis has an equality statement, and then the alternative has this not equal to. Okay, that's a feature of the two-tailed test. A one-tailed test, now keep in mind that for all null hypotheses, equality is always there. Equality is always in the null hypothesis. But if you run a one-tailed test, you also have to keep a direction in there too. So if I go up here and say, okay, I'm going to keep the equality statement here, but I also think this is what I've got here. I think I'm greater than this 0.67. That means the null hypothesis has got to be the opposite of what I'm interested in. So it's going to be the equal to or less than that 0.67. Remember, we test the null, not what we want. So if I test and I say, ooh, you've got evidence against this, guess what I conclude? I conclude the alternative. What does the alternative say? You are greater than 0.67. And that's where I thought it was going to be. I know it's backwards, it's loopy, but that's how you actually test a hypothesis. You test the opposite of it, you find evidence to reject it, and when you reject it, the question should be, wait, you're having me reject what I thought it should be, well then what's left to conclude? And that's where you say, well, you ought to conclude that the mean is greater than 0.67. And that's how you logically get someone to arrive at what you think the right answer is. You get them to reject what they're thinking and only be left to conclude what you are thinking. Yes?
So you should go through all of these steps, like the one-tailed test.
We go through these steps. We're at the state the null hypothesis. So the question is, what kind of hypothesis will I propose? A two-tailed test or a one-tailed test? And we're just going through the reason for why we're choosing a two-tailed test. Yeah. Good question. So this is how you write it. Mu is equal to 0.67 for the null hypothesis. Mu is not equal to 0.67 for the alternative.
How would you come up with that 0.67?
How do we come up with the 0.67? Well, as we were reading in the, well, if you read the full article, that the proportion of kids who are receiving preventive dental care in the UK, at least over the past 1 or 2 years, is about 0.67.
Okay.
So we're going to take that value.
That's the percentage, okay.
Yeah, we're going to take that value and make that our null hypothesis. Because what we want to be able to say is whether the US is significantly different from the UK, significantly higher too. That's what we think. That's what we hope we'll be able to say. Then we need to select the sampling distribution. What's the underlying math? We think it's going to be normally distributed. So we say we think we're going to use the sampling distribution. A normal distribution with a mean of, oops, that should not be 2.53, that mean should be 0.67. Mean of 0.67. And at alpha 0.05, we'll say half of that error goes down here and half of the error goes up here. You good so far? Okay, the next step is Jamovi, because we have to compute the test statistic. I know what my underlying distribution is, I know what my mean is, I know what my hypotheses are. You have Jamovi open?
Yes.
So let's get in there. When you open up Jamovi, what Jamovi will not show you is what the formula is for calculating that test statistic. This is the formula. X bar minus mu divided by, and down here, this whole thing is called standard error. Not standard deviation, but standard error. And what we're doing is we're taking the standard deviation from our sample and dividing it by sample size minus 1. What's the square root of that? And so this error estimate, as you can tell, the larger this n is, the smaller this number is. And the smaller this number is in the denominator, the bigger this t value will be. And the bigger this t value is, it tells us the further out we are. All right, so Jamovi, for the proportion of kids receiving preventive dental care, you're going to use the Lab 2 data.
Lab 2? Okay.
Yes, Lab 2 data. Last data. And what we want to select, up in the top left, for your t-tests, there are 3 of them. One sample t-test, paired sample t-test, and the independent sample t-test. And there at the bottom, the one sample t-test is what we want to run. One sample t-test. So let's select that. One sample t-test. And then it asks you, well, what's your dependent variable? And our dependent variable is going to be the 2016 data.
The kids.
2016 for the proportion of kids receiving preventive dental care. So let's stick that over there. That's our dependent variable.
Got it.
Now we need the actual statistics so that we can answer the questions. So over on the left-hand side where it says tests, we want that student's test, student's t-test. Okay. Let's ignore the Bayes factor for right now. Yes, question?
So in the beginning you put variables kids prep 2016,
Yes.
and then for split by
Now we're not going to do a split by because
No.
we're over here in t-tests.
t-test.
We're over here in t-test where we're going to run a one sample t-test. So we won't do a split by. We would actually have to run a filter in Jamovi if we wanted to only look at one region. So Kids Prep 2016, we want a student's t-test, and over on the right-hand side where it says additional statistics, we want the mean difference, so we know how, if there is a difference, how much of a difference is there between the US and the UK. We want the effect size, remember the t-shirt size, a small, medium, large? Or we were talking about the size of the tool you're looking for in the garage? That's effect size. So we want a calculation of effect size to figure out how large is this tool that we found, or this difference that we found. We also want a 95% confidence interval. Now this 95% confidence interval says look, you went and calculated a difference between the US and the UK. Now, are we sure that that's the exact true difference? No, we don't know. So what we'd like to do is build an interval around that calculation where we say, look, if we did this 100 times, went to the US, pulled out the sample, and compared to the UK. Again, go to the US, pull out a sample, compare to the UK. Again, go to the US, pull out a sample, compare to the UK. If we did that 100 times, 95 out of those 100 times, that interval would have the true value in that. So we're only going to do it one time though. We're not going to do this 100 times. We're only going to do it one time. So we call it a 95% confidence interval, where that one interval we think has the true value in it. So I'm going to calculate what the true value is, what the true difference is. But I'm also going to put an interval around it because I'm not 100% sure. And finally, down in the middle where it says hypothesis, this is where we need to tell Jamovi's one sample t-test. I'm going to compare to the UK. And right now, Jamovi is saying, well, is the proportion of kids receiving preventive dental care 0? You say, no, it's not 0. It is 0.67. So we're testing against 0.67. It's also asking, oh, what kind of test are you running? Because I need to know what kind of p-value to give you. Is it a one-tailed test or a two-tailed test?
Two-tailed.
You notice here, the top option says equals test value.
That's a two-tailed.
Because it's telling us it's a two-tailed test, or we're telling you it's a two-tailed test. If you want a one-tailed test, you can pick the other options. This is a two-tailed test. Guess what? You're almost done. We have to test that one last assumption, normality. So down here where it says normality, the Shapiro-Wilk test, let's select that. Got it. Now we're ready. Let's look at what we've got. Now, we don't have any pretty tables, we don't have any pretty figures because you've already done that descriptively. You've already characterized and described the proportion of kids receiving preventive dental care in the US in 2016. Now, those were your observations. Now we're trying to find out if our observations are due to random chance or something else. So let's look at our one sample t-test results. First, it tells you what your variable is, which is the proportion of kids receiving preventive dental care in 2016. And then it tells you what kind of statistic it's going to give to you. And this is called the student's t-test. And as you look at the student's t-test, the statistic tells you it's 27.5. Now, this is a standardized score. A standardized score. Essentially what it's telling you, hang on, I need to come out of here, and then I need to come back, not there, not there, apologies. There we go. It is telling you that this score, when I take the US's value and subtract the UK's value from it, and divide by the standard deviation for the US, and then divide by n equal to 51 minus 1, this whole thing is 27.5. That's ginormous on that distribution, right? Because our scores are saying, if you look down here, 95% of the distribution is between a -2 and a 2. And we're saying our test statistic is what? 27.5. Where's 27.5? Off the charts. Off the charts. So it's telling us you have a really, really statistically significant difference. Or as we go back to the other slide, did I give you a slide of how to interpret the p-values? If you were less than 0.05 or less than 0.05. So this would be what? What kind of evidence against the null hypothesis?
Strong.
No,
No, against weak. No.
No, not weak.
You say
The
against?
top, yeah, against the null hypothesis. How
No
much?
evidence.
Overwhelming. This is overwhelming evidence against the null hypothesis. So that Strawman, it's like you gave it a wild combination of da, da, da. This is overwhelming evidence against the null hypothesis. That's how you knocked it down. It is a knockdown, like one KO punch, down, out, not coming back. 27.5 on this scale. Not coming back, all right? So that's what the T statistic is telling you. How far out? Think about it like a Z-score. Yes. Yes.
You know you have the two-tailed test?
Yes.
I know that it's overwhelming on one side. What is the other side? You
No,
don't have to worry about it.
don't have to worry about it. Don't have to worry about it. Because you said, look, it's almost like when you were knocking down the straw man, you said, okay, now tie your left hand behind your back, right? Because you don't get to use your other hand. So you tied it behind your back, and then with your other arm or your other hand, you gave it the knockout punch. You say, well, what about the other hand? Nobody cares about the other hand. With one hand, you knocked out that hypothesis, right? So no one cares anymore about the other side. We know that we're on this side, and you're way out there. Yes?
So if it were in that very shady area, then
Yes.
you would care about the other side? Or
We're in that gray zone, but we're so far out in that gray zone, it's so tiny, the area under the curve, and we're way out, way out there.
my question is, when do you consider the other side?
We don't, because when you actually say, where are you in the distribution, automatically say, who cares about the other side? It's before you test, you say, okay, I actually care. It's like when you get in an accident, right? The insurance company wants to know, so where did it happen, like in the front or in the rear? And when you tell them, well, I was rear-ended, you're also going to ask, well, what happened in the front? But at some point, they'll say, who cares about that anymore? What was going on behind you? And weren't you looking back there? Blah, 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 et cetera, et cetera. Okay, so once we know where things happen, that's where all of our attention is going. That's where we are right now at 27.5. Now, before we go further, what is our assumption test telling us? The Shapiro-Wilk test. The p-value for that is what? 0.033. It's telling us that the null hypothesis for the Shapiro-Wilk test, not the one-sample t-test, for the Shapiro-Wilk test, it's saying you have to reject the null hypothesis because it's less than 0.05. Now the null hypothesis for the Shapiro-Wilk test is normal distribution. But we're having to reject that. Why? Do you remember what that looks like? If we go back to explore or exploration, top left, go to exploration, descriptives, and you take your Kids Prep 2016, you put it in variables, and you ask for down in the middle where it says normality, ask for Shapiro-Wilk. I get the same value, which you should, 0.033, and then you ask for a histogram with its density curve. Remember, you've done this already. We're just jogging your memory. You got this kind of distribution. Does that look like it's normally distributed? No, it doesn't. In fact, it looks like you have two normal distributions there. It's bimodal. You have this normal distribution up here and this one down here. And that's why the p-value is 0.033. So when you look, one of my assumptions for this test is I want to build a map based off the normal distribution curve. But the test is saying it doesn't look like it's normally distributed. It looks like something else is going on. And when we look at the history, we say, well, yeah, it does look like something else is going on. It looks like I have two distributions there. So the question is, will I proceed? And in this class, yes, we're going to proceed. We're going to make an assumption that despite the fact that the test is telling us it's not normally distributed, we still feel like our conclusion will still be warranted. That is that it's somewhat normal, it will behave with a skew, but it'll behave so that I can make a decision. The other way that we test in practice, though, is that when we have to violate this assumption, we look for what's called a non-parametric test. A test that says, you know what, we're not so concerned about that underlying distribution. We're just going to rank the scores and kind of see how the scores compare. And from there, we'll test your null hypothesis. Okay? But we'll get into that later. So right now, I just want you to understand, why is my Shapiro-Wilk telling me 0.033, I have to reject null hypothesis? Because this is what the distribution looks like. Bimodal. It looks like you have two normal distributions. In practice, what you'd probably do is, one, test with a non-parametric test, or two, split your distribution right there and say, I'm going to look at this half, and then I'm going to look at that half. So will we proceed? Yes, we're going to proceed. Go back to your t-test, one sample t-test. Unfortunately, you'll have to put Kids Prep back into your dependent window, ask for your additional stats again. Thankfully, Jamovi is very easy. So you don't have to worry about taking too much time to put that back in. Okay, so in terms of our test for normality, we reject normality, but we're going to proceed. It was an assumption we made, but we're okay with proceeding. And as we proceed, we see that DF is 50. Anyone have an idea what the DF is? I'm not going to assume that you've already made it that far in your other book, because it kind of spells out all these different things. Not descriptive figures. Degrees of freedom. Degrees of freedom. Now, if you think about that term, degrees of freedom, it's like how far can I vary? How much freedom do I have? And what we're saying here is the degrees of freedom, when we compare it to the sample size, is less. I started with 51 states or regions contributing. But my degrees of freedom says you've taken one away. It's that n-1 for this one sample t-test. And what we've done is that we've increased the rigor into our test. We've handicapped ourselves. Remember, a larger sample size gives you more power, right? We've taken power away. We do this every single time with all of our stats tests. We say, let's take one away from each group, and right now we have a large group. Take one away from each group, and then let's see how you do. Because we want to see if there's enough power in your data to reject the null hypothesis. So it's a standard handicap every single time we test a hypothesis. We're dealing with uncertainty. We don't know everything. So one of the ways that we can build in for that uncertainty is just take some power away. So we take an observation away, take a sample size away, and then proceed with our tests. So that's what degrees of freedom is. So you report degrees of freedom. So people say, ooh, how much did you handicap yourself when you ran this test? All right, so our test statistic, 27.5, off the charts. Degrees of freedom, still pretty large, even though we handicapped ourselves because DF is 50. Our p-value says what? What is that p-value? Less than
0.1%.
less than 0.001. So in terms of evidence against the null hypothesis, what is this? Overwhelming? Is it significant? Is it weak? Is it strong?
It's overwhelming.
This is overwhelming evidence against the null hypothesis now for the means. That is the difference between the UK and the US. We have overwhelming evidence that suggests the US is not like the UK. The US does not come from the UK distribution of proportion of kids receiving preventive dental care. This isn't a geographical question. It's just saying, hey, in terms of the proportion of kids receiving preventive dental care, does it look like the US and the UK have similar processes going on? No, it does not. The US does not look like they came from the UK population. In terms of the mean difference, how much of a difference between those proportions is there? What did Jamovi calculate it as? 0.138. So convert that to a percentage. 13.8%. So that's how much of a difference there is between the proportion of kids receiving preventive dental care between the US and UK. 13.8 percentage points. Now, are we certain that it's 13.8? Are we absolutely 100% certain that it's 13.8?
95% certain.
We're not sure. But we could build an interval
Yeah, it went away.
around the true value.
It's about to die.
I could build an interval around it, and that interval says it will range from 12.8 to 14.8%. So I calculate it as 13.8, but a 95% confidence interval says that the true value between, or the true difference between the US and UK is somewhere between 12.8 and 14.8%. And what we really like about that is how narrow that interval is. It wouldn't be very meaningful if that interval said, oh, well, we're quite certain it's somewhere between 1% and 56.2%. That's not really helpful. But what we got is somewhere between 12.8 and 14.8%. Like, wow, okay, we have a pretty good idea of how much of a difference there is between US and UK with a 95% confidence interval, which tells us that if you did this 100 times, 95 or 100 times, that interval would have a true value. How are we doing so far? Yes?
I think knowing this, I think I understand the test better.
Oh, retrospectively? Okay, well, that's good, because we have one more coming up, final exam.
Is that like the same format?
Same format for the final exam? I'm hoping so. I'm hoping that I'm allowed to give you a take-home exam, but I'm not sure if they will allow that.
We can keep it between us.
I don't think I would be able to keep it
On
from
the
the
deal.
fifth floor, so.
So
You can
if
keep
it's
it on
not
the
take
deal.
home, can we do like a group?
I don't know about a group. I mean, what we could do is, I mean, we could have a portion of it that's take-home, and then what we do in class for ExamSoft is not meaningless, but is something.
Like vocab and.
Maybe. We can work on that. We have time. But the question, will it be similar? Yes, in the sense that straightforward questions I'm at. Oh, low battery. Is that what you were telling me?
Yeah.
Oh.
It's been keeping us on edge for the past 15 minutes.
We are going to finish up soon. All right, let's get in there. All right, so 12.8 to 14.8%. Look at Cohen's D, 3.84. Remember what we said was a large effect size in terms of Cohen's D? We said anything above 0.8 was a large effect size. Here we are at 3.84, which is really, really big. Really, really big. Very big. We're going to come right here, Cohen's D. Anything above 0.8 is considered to be a large effect size.
When
You
did
know,
we
the size
say
of
that?
When we were talking about power, we were talking about looking for tools in the garage and how messy the garage was and how big the tool was.
Okay,
Effect
that's
size,
it.
we said, was anything above 0.8 was big. Between 0.5 and 0.8 was moderate or medium. And anything less than 0.5 or 0.4 was considered to be small. Yes?
What the Cohen's D is?
Cohen's D is the size of the effect. How big is the tool? How big is the tool that you're looking for in the garage? And here, we're saying it's ginormous. And it's a standardized version of how much of a difference is there between the US and the UK. So one way to think about it is with this t-statistic, but that's a hypothesis testing way. The other way is looking at it like Cohen's D. Cohen's D is saying it's pretty big. Yes, question?
Like I want to learn again. So you said p-value is too, if the p-value is too overwhelming because of the 95% of the computation introvert, like lower upper, it's still okay.
Right, so the UK is at 0.67. 67% of kids are receiving preventive dental care. And the US is at 0. I'm going to go back to our t-test, one sample. And I'm just going to put in our descriptives before my battery totally quits on me.
Do you need a charger?
No, we're almost done. No, thank you though. It was very kind. That came out way too passive aggressive, sorry. So we are here at 80.8%. So the US, UK is at 0.67. US is at 0.808 or 0.81. So 67% versus 81%. In terms of the standard deviation and standard error, that 67 to 81%, or that 13-14% difference, is considered to be really large, really big. That's why the Cohen's D looks so big, that's why the p-value looks so small, and that's why that t-statistic looks ginormous. It says you're way off the charts here. There's no way you come from this distribution. You come from a totally different distribution. That's what those numbers, this quantitative number, actually tell us.
But then at the same time you said, but you
Right.
can bring it up. I mean, but we can use this because of the got it on like 95%.
Yeah, so the 95% confidence interval says, I calculated the difference as 13.8%, but I'm not 100% sure that it's 13.8%. So we can build an interval around the true value. I don't know where the true value is, but I can build an interval around it. And that 95% confidence interval says, well, it's somewhere between 12.8 and 14.8. That's how you test. That's how you test the one sample t-test. Now, I need to very quickly get into not that one. That one. That one. How do you write this up?
That's a good question.
Oh, it happened.
How does that do that?
This is how you write it up. I'm going to talk really fast because you have it written there.
Okay.
Yes.
Single sample t-test was conducted to determine if a statistically significant difference existed in the proportion of children receiving dental care existed between reported values for the United Kingdom and observations made in 2016 in the U.S. The proportion of children receiving dental care in the U.S. was statistically significantly higher by 13.8%, with a 95% confidence interval between 12.8 and 14.8%, as compared to the UK level of 67%, with the T of 50 equal to 27.5, P less than 0.001.
Okay.
Right? That's what you want to write. That's your conclusion for the one sample t-test. So for your homework, I'll send that to you. You do that for 2007 and 2011, so you get the hang of it. But this is what you do. So next time someone asks you about the proportion of kids receiving preventive dental care, you can say, well, actually, at least as measured by 3 years ago, US and UK are quite different. In fact, statistically different. Question is why? Why is it so different? And that's where other research would be needed. But what you've demonstrated, which has not been reported, is that we differ statistically and clinically. I think a 13.8% percentage point difference classifies as something
Are we
clinical.
going to use this formula for the homework?
No. That's what's running under the hood. Like we all drive our cars, but we don't really know the algorithms that are responsible for the combustion exchanges. So, yeah, this is what's running under the hood. There is an algorithm, there is a formula, but what we want to understand is what comes out of the back end. And that's those tables for the results.
Are we gonna use pretty much the same?
That same
Wording?
template, yes.
Yeah.
Just take that, it's a template now. So this is the part that the clinicians actually like. Tell me exactly how you want me to do it. This is exactly how I want you to write it. So this is not the literary form that Henry James would approve. This is the literary form that we're going to get through for scientific technical writing. Copy it, just take out the bits and put in the new bits for 2007 and 2011. But copy the exact structure. And this is what we get for every single test, the exact template that you have to follow. Yes?
95%.
Confidence interval. Confidence interval.
Do we have it on a table?
Yes.
Yes. So when you ask for it in your Jamovi, it says, what do you want? You say, I want the mean difference, I want the confidence interval, and you say, yep, give me that. Other questions?
Are you posting this one?
Yes, I will post the homework assignment. Oh, and before we go, so I'm going to close this, because
Yes.
I am a little passive aggressive. I want to be the one to close it. I don't want the battery to go out on me. Next week, you will have access to a lecture that's pre-recorded. I won't be able to be with you next Tuesday. And we couldn't find a time that would work for the entire class for Monday or for another time this week. So there will be a recorded lecture in the module that you will look into, and it's pretty much just a guided course or a guided step-by-step for how to do the next test in Jamovi. Okay, so we won't be meeting next Tuesday, which I understand gives you the entire morning free. Is that correct? You do get the time? Nice. But there will be a lecture for you to get through in order to guide you through the steps of the next statistical test, which will be parity test and independent sample test. Any questions for me? Nope. Alrighty, I'll see you guys. I see some of you a lot sooner because of our research.
Hey.